Good morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, we are going to discuss about the examples in second unit, that is transmission line 2. In the last class, we completed the examples in the unit 1, transmission lines 1. Now, you can start the examples in the second unit, that is a transmission line 2. So the first example, a line with zero dissipation. A line with zero dissipation has R is equal to 0.006 ohms per meter and L is equal to 0.25 microfarad per meter, and capacitance is also given in the picofarads per meter. If the line is operated at a frequency 10 megahertz, find R naught, nothing but it is a Z naught, the characteristic impedance, and attenuation constant alpha, phase constant beta, and V is a wave propagation and the lambda wavelength. Got it, my dear students? And so first is given all the primary constants R, L, C, R, L, and C, and also the frequency given 10 megahertz. At 10 megahertz, omega is equal to 2 pi f. Okay, omega is equal to 2 pi f. And it is multiplied with the L. What is the L we given? It is a 2.5 into 10 to the power of minus 6 N per the meter. Totally you can find out the omega L is equal to nothing but 2 pi f L. 2 pi f is given the 10 mega 10 power 6, and 2.5 into 10 power of minus 6 is a inductance. The totally we have omega L is a 15.70 ohms. We know the omega L is very much greater than the resistance R. At 10 megahertz frequency, omega L, now we got the 15.7. What is the resistance here? 0.0006. So which is definitely the omega L is greater than the resistance. So according to the standard assumption of for the dissipation-less line or the lossless line, we can neglect the R. We can neglect the R. Then you know the characteristic impedance in terms of that is R naught is a root L by the C. Root L by the C. Where L is given, it is a 2.5 to the power of minus 6, and C is given 4.45 into the pico 10 power minus 12. The substitute, and you can find the first one is R naught, and nothing but the Z naught, the characteristic impedance, and the propagation constant. We are saying it is a lossless transmission line. Alpha is equal to 0. The gamma is equal to alpha plus j beta is nothing but the 0 plus j omega root LC. What is the omega here? The 2 pi f. F is 10 into 10 power 6 because the given is a 10 megahertz. And under root of L is a 2.5 micro 10 power of minus 6. And C, the pico 4.45 into 10 power of minus 12. And calculate the value. We'll get gamma is equal to 0 plus the beta value 0.2095. The attenuation constant alpha is equal to 0 and the phase constant 0.2095 radian per meter. And this value is a Napier per meter. Napier per meter. Right, is a Napier, not the Newtons. Napier per meter. And the velocity. The velocity is, we have the formula is 1 by root LC. 1 by root LC. Substitute L value and the C value, can find out the 2.998 into 10 to the power of 8 meter per second is approximately 3 into 10 power of 8 ohm. And wavelength lambda is equal to wavelength lambda V is equal to F lambda, or lambda is equal to V by the F, and we can substitute the V is a 3 into 10 to the power of 8, and the frequency is given the 10 into 10 power of 6. Okay, you can get the value of the lambda, or otherwise the wavelength is given by gamma is not the gamma. V is lambda is equal to, or the beta is equal to, we know the 2 pi by the lambda, or lambda is equal to 2 pi by the beta. Substitute the beta value and find out the value is at 2.29.9913. You can use any one of the formulas to find the wavelength lambda is equal. Got it? So in this, we find the Z naught by saying that is omega L is very much greater than the R. And here there is the standard. So according to the standard assumption for the dissipation-less line, we can neglect the R, and that it is a lossless transmission line. Alpha is equal to 0. Then the Z naught, gamma, propagation constant in the detonation constant is alpha, and the phase constant is a beta. The wave velocity, not the wave velocity. Okay, wave velocity only. The velocity of propagation. Okay, V is equal to in terms of L and C, and the wavelength also in terms of the beta or in terms of the F lambda. V is equal to F lambda. The frequency we know, and the velocity is also we know. By that values you can find out the wavelength, or otherwise 2 pi the beta is another formula we have. The 2 pi by the 0.2095 can substitute as a beta. We got a radians per meter. 29.9913 meters is the wavelength. Okay. And next example. A certain transmission line working at radio frequencies. A certain transmission line working at radio frequency. We know the radio frequency, neglecting of the terms R and neglecting the terms of G, the Z naught is equal to L by C on. Okay. Working at the radio frequency has the following constants, L and the C. L is given in terms of the 9 microhertz per meter, and C is 16 picofarads per meter. The line is terminated in a resistive load. Resistive load means it is a ZR. ZR is given. Find the reflection coefficient and the standing wave ratio. The reflection coefficient is a K. Nothing but is a magnitude of K you can find. And standing wave ratio, yes. There is a relation between of standing wave ratio and the reflection coefficient K also. So first of all, to find the Z naught, then only we'll get the reflection coefficient and the standing wave ratio. The reflection coefficient is ZR minus Z naught by ZR plus Z naught. Otherwise, S is equal to 1 minus the magnitude of K whole divided by the 1 plus the magnitude of K. The reflection coefficients. Okay. See, the previously we got this the same thing. It's a plus is a numerator and denominator is a minus. Sorry, and here is a minus. The S is equal to E maximum by the V minimum. The S is a standing wave ratio and the K is a reflection coefficient. Using this, you can find out the reflection coefficient and the standing wave ratio. First of all, by using L and C, the characteristic impedance Z naught is equal to R naught, that is the root of L by C. Given it is a 9 micro, 9 into 10 to the power of minus 6. and C is a 16 into 10 to the power of minus 12. Simplify this, you'll get the 750 ohms. Then the reflection coefficient K is equal to ZR minus Z naught. ZR is given the 100 ohms. We got the Z naught, not the 100 ohms, sorry, 1000 ohms. 1000 minus 750 by 1000 plus 750. 250 by the 1750. You can calculate 0.1428. The reflection coefficient. And the relation between of reflection and the standing wave ratio is the E maximum by the E minimum. 1 plus the reflection coefficient by 1 minus the reflection coefficient. You can substitute the value 1 plus 0.1428 and 1 minus 0.1428. You get the 1.333. Got it, my students? The next example, a certain radio frequency transmission line, a certain radio frequency transmission line is terminated in a pure resistive load. The characteristic impedance of the line is given the 1200 ohms. Characteristic impedance means Z naught. Z naught is given as 1200 ohms. And the reflection coefficient was observed to be the 0.2. Reflection coefficient is a K, given is a 0.2. Calculate the terminating load. Terminating load means ZR. ZR is equal to how much? Which is less than the characteristic impedance. Definitely, where ZR is less than the Z naught. Okay. Now at the radio frequency, S is equal to R naught by RR. R naught, nothing but here it is a normalized impedance. Let us take here. Okay. R naught by RR. R naught is given this Z naught value 1200 by RR for resistive load. As of in the radio frequency, S is equal to the standing wave ratio. We already know the S is equal to, saying that it is a E maximum 1 plus the K by 1 minus the K, the reflection coefficient. Now the relation between these two, so S by 1 is there. You can divide the component dividendo S minus 1 by S plus 1. And in this, the denominator value is 1 plus the magnitude of K minus, you can take as a 1 minus of the magnitude of K whole divided by 1 plus K, not the 1 plus K, it is 1 minus of K, the magnitude, plus 1 plus the K value. Got it, my students? So this is a component of dividend we can apply here. Whatever the denominator is there, subtract in the numerator and add with that numerator. S minus 1, the same thing as an S plus 1. Here also the denominator is 1 minus the magnitude. So with this the value 1 plus K minus 1 minus of K. And same thing 1 plus K you can take plus 1 minus K. Okay. If it is a confusion, I will write again. What is the value in the numerator? 1 plus the magnitude of K. In the numerator, we are subtracted. Now in the denominator, you can add the term. 1 minus the magnitude of K. So minus and the minus is get cancelled. And in the numerator, 1 minus 1 is get cancelled. 2 the magnitude of K whole divided by the 2. The 2 to get cancelled. K is equal to S minus 1 by S plus 1. Okay, that is a relation we are using here. So K is equal to S. What is the S here at the radio frequency? S is equal to R naught by RR. That is a 1200 by the RR minus 1. And similarly, the S is 1200 by R plus 1. So take this as a K is equal to, we got the given the reflection coefficient is a 0.2. From this, we can find out the RR is equal to. Simplify for RR, we get what is RR? The 0.2, the K is equal to, and 1200 minus RR, and in the denominator 1200 plus RR. Both the denominator is the same, we get cancelled. And now the 0.2 you can multiply with the 1200 plus 0.2 with RR is equal to 1200 minus RR. Now I can bring this in the towards the right side and bring this towards the left side. This plus 1.2 RR is equal to 1200. Take the common 1 minus 0.2. Okay, therefore RR is equal to 1200. 1 minus 0.2 means it is a 0.8, I think, by 1.2. 1.2. Let us take it is in terms of 0.8 and here the 1.2. 8 by 10 and 1.2 by 10. 10 get cancelled. You can write this as RR is equal to 1200 into 8 whole divided by the 12. Okay, so 0.8 by 10 and 1.2 by the 10. So it's 8 by 10 and 12 by 10. Nothing but is a 0.8 by 1.2. So 12 here is a 100. R is equal to 800. We got RR is equal to 800. So definitely, if it is a reflection coefficient, what we are saying here, the ZR minus Z naught by ZR plus Z naught. Okay, what is the ZR here? We got RR nothing but 800 minus 1200, which is saying that it is a calculated terminating load which is less than the characteristic impedance. Less than the characteristic impedance. Definitely, the characteristic impedance is at 1200, and now we got the terminating load. The calculate the terminating load which is less than the characteristic impedance. So here we can take it is a 800 plus 1200 is a 2000, and minus 1200 minus 800 is a 400 here. By the 2000 and 2 get cancelled here, 2 zeros, and the value is a 1 by 5. 1 by the 50, not the 5. 4 5 only, sorry. 4 5 is a 20. 1 by 5. So 1 by 5 means you can write as is a 0.2. Got it, my students? So the less than the value, so it satisfies the condition also. So RR is equal to 800 by using this formula. Then go for the next example. Calculate the standing wave ratio and the reflection coefficient on a line having Z0 is equal to 300 ohms and terminated in the ZR is equal to 300 plus J into 400. Okay. They are asking finding out the S standing wave ratio and the reflection coefficient K for the given Z0 and the ZR. The reflection coefficient, we know the formula is ZR minus Z0 by ZR plus Z0. ZR is given 300 plus J400 minus 300 and 300 plus J400 plus 300. So in the numerator, 300 get cancelled, J400. In the denominator, 300 plus 300 is a 600 plus j 400. Okay, my dear students. I think we can take the 0 plus j 400 in the numerator and 600 plus j 400 in the denominator. Otherwise, we can leave this function as 0 plus j 4 whole divided by 6 plus j 4. Means in the numerator I take the 100 as a common and denominator is also 100 as a common, and still you can simplify this value 0 plus j into 2 by 3 plus j into 2. So numerator you can find in terms of the polar form, and denominator it's also find in terms of the polar form. What is a polar form? Under root of r square plus x square plus y square. Okay, x square 0 square plus 2 square with an angle is tan inverse y by y is a 2, x is a 0, means a 90 degrees here in the numerator, and in the denominator 3 square plus 2 square and angle is a tan inverse 2 by 3. And now in the numerator you can see the 2 square, 0 square plus 2 square is a 2 value only, 2 with an angle of 90 degrees, and denominator 3 square is a 9, 4 square 2 square is a 4, 9 plus 4 is a 13, under root of 13, and angle tan inverse 2 by 3. You can find out the angle 2 by 3 to get is a 33.69 degrees. Calculate the 2 by 13 and 90 minus 33. 90 minus 34, let us take it is a 6.34. You can subtract 6 and 3 here. What is a 4? 5, 56 around. So 0.55 with an angle of 56.31 will get the reflection coefficient. So the standing wave ratio and the reflection coefficient having the relation is there. 1 plus the standing wave ratio reflection coefficient by 1 minus the reflection coefficient. Okay. So 3.4913 is the standing wave ratio for the given Z0 and the ZR. Got it, my dear students? Okay. The next example is see, this is already I explained the switch chart having the R circles like this. The outermost circle is a 0 circle and goes on increasing the value 0.2, 4, and so on is go on increasing. It is an infinite line. Got it? 1, R is 5 and R is 20 and so on. And here the half circles are there, the X circles. So the line whatever showing here is X is equal to 0. Increasing we are going like this 0.4, 0.6, 0.8. Let us take it is a 1, 2, 4, 10 and so on. The last value here it is infinite. Here also the AR circles is also you get the infinite. Both these two in the right hand side is infinite value and the left hand side the least value. So always we can take here the V maximum towards the right side and V minimum in the towards the left side values. Okay. Combining the R and the X circles, you'll get the basics of the Smith chart circle diagram. So the x0, the 0.5, the 1, 2, and so on is combining of x circles and r circles with the degrees also. So 180 degrees, the 90 degrees, 45 degrees, and 35 degrees like this, increasing the value. Okay, combining r and the x circles. Suppose if we have the normalized impedance, what they are saying here, this line is a 0.5 line. Okay, 0.5 x circle. So, and this circle is one circle. So, at this point, r plus j into x. What is r here? 1.0 plus j. What is the x here? 0.5. It's a 0.5. Suppose if this point is here, if the point is here, the normalized impedance, what is r here? R circle is 0.5 r circle. So 0.5. What is the x circle here? X circle is a 0.5 only. J 0.5. Suppose I move here itself, or otherwise here itself. What is this circle? This R circle is a 0.2. R circle is a 0.2 plus X circle is a half circle is there. Already is a 0.5 and this increases 1. So J into 1.0. Suppose the same point is there in the bottom line. Suppose here we can check this is becomes of 1.0 minus j into 0.5. Got it, my distance? Only the change here. Similarly, if I use this same circle is in the bottom line, below the bottom line, is a bottom line, my dear students. So assume this is a bottom line. Above the values is a positive values of imaginary, and below the values is a negative value. Suppose if I am assuming this one, the same thing 0.5, but before it is a below the bottom line means minus j 0.5. Okay. Suppose if this yellow mark is there, if I use this one at the point here, this is a 0.2 of R circle minus j into 1.0 of the X circle. Got it, my dear students? Like that, you can assume where the point we got as a P. P means from origin to plot a point P as a normalized impedance, that is ZR by the Z naught, nothing but it is a Zn normalized impedance, and extended this point up to the value of point M. Take the distances of OP by the OM or OQ. Let us take if it is a Q also in some textbooks are mentioned with the Q, or in some textbooks that is a M. Okay, OP by the OM value. Understood? So the constant X circles and R circles we have. You see the maximum of what I shared is X and R is both are X and R is both are in the infinite value. So with the maximum, and X and R is in the left hand side, both are minimum. So it is a V minimum. Okay, my dear students. See the example here, the given. Consider a 30 meters long lossless transmission line with a characteristic impedance of 50 ohms operated at the 2 megahertz. If a line is terminated in the impedance 60 plus J40, calculate the reflection coefficient, the standing wave ratio, the input impedance if the velocity of line is V is equal to 0.6 C. These are the theoretical calculations. K is equal to ZR minus Z0 by ZR plus Z0, and K is equal to 1 plus K by 1 minus K, and velocity V is equal to W by beta, and beta is beta S. To find the Z in input impedance, the tan beta S, all the velocity, the standing wave ratio, and the reflection coefficient you can find by using critical values. We already seen in the Smith chart. Okay. Now we go for to find on the Smith chart, ZR is RR plus J into RR. As of normalized impedance, I told 1.2 plus J into 0.8. This is above the bottom line. Okay. And we can find out the reflection coefficient and the input impedance of the lines by using the Smith charts. We'll get this is a Smith chart. I told 0 to P and the P to M value. The ratio between of OP and the OM will get the magnitude of the reflection coefficient, and angle is whatever the bottom line here is a theta R. So the reflection coefficient is equal to the magnitude of reflection coefficient with an angle of theta R. To get the magnitude of the reflection coefficient is the distance of OP by the distance of OM, and the theta R will get from this here. This is the theta OP, and extended the value is the M. With the distance of OP and OM, we'll get the reflection coefficient gamma, and angle with theta, and with the distance of O to P, draw a radius, not the draw a circle with radius, sorry. Draw a circle with the radius of OP. Okay, my dear students. Draw a circle with the radius of OP, and if S is wherever the circle is meets in the real axis of S, real axis the point here, that R circle is meets with the OP radius of the circle, nothing but is a S circle. It is S circle. S is equal to, theoretically we got it is a 2 point something. Here we will get the 2. Got it, my distance. And then we can extend it this value here, this line, not the value, sorry, extended this line. And there is another point here, the O to P. Now we can mention this of P dash. Here the point P, there is a ZR by the Z0, nothing but the normalized impedance Zn. Here at the P dash will get normalized admittance Yn, normalized admittance Yn. Okay, my dear students. Like that, we can find out the reflection coefficient, the standing wave ratio, and Zin also. Zin is equal to Z0 into ZR minus J into tan beta L or the beta S. Zin is equal to Z0 whole multiply with ZR minus J into tan beta S or the beta L, the length, and Z0 plus J into tan beta L. Using this, the length and the beta value, you can find out the angle. We can extend it. This is a 50 degrees we got as a theoretical value. Here also approximately you have to get the 50 degrees. And from this line, you can take the circle here up to that to get the Z in value. So wherever it is gets the degrees following the degrees values, then we'll get the, by using the Smith chart, we'll get the Z in value. Got it, my students? So like that, by using the Smith chart, we can find out the reflection coefficient magnitude and the theta, the totally the reflection coefficient gamma. S is equal to the standing wave ratio, and similarly the Z in also. Got it, my students? You see here, in this the magnitude of K is a 0.35, and the phi is equal to 55.5, S is equal to 2.1, and Z in is equal to 24 plus J into 1.75 ohms. So the three will get in this Smith chart by using this Smith chart. Okay, my dear students.